Swayam Prabha. Digital India. Educated India.
So in the last lecture, we are looking at a case study about microprinter and 3D microfabrication and some kind of a technology for that, and how Mechatronics very elegantly helped us to realize that the goals of that 3D printer. So today we are introducing some other case study where we are looking at this Hele-Shaw based system for a very interesting way of fabrication. Okay, so this is again invention at our lab, the Suman Mashwal Advanced Microengineering Lab, and with some patents pending on this technology also. So I'll tell you why we are looking at these technologies and what are the utilities for some applications as we go along. Okay, so let's begin with the so this is the lab where this activity was carried out, and we have seen here some of these micro 3D printing components that we have seen in the last class. Okay, so there is a lot of collaborative work going on in this lab with different places, and maybe I'll have some opportunity to talk about a little bit about that also. So why we thought of like getting this new way of fabrication is basically the inspiration is nature. So in nature, a lot of systems you can see have these branches which are splitting branches. Okay, so the trees has like this main branch splits into some branches, and further they split into branches, further they split into branches, and there is some reason for such kind of structures. If you see the mass transport activity or the heat transfer activity, these activities are very efficiently done by these kind of structures. Okay, say for example in our heart circulatory system also we have these branches, multiple branches, and then split happens here, and that's where the oxygen and carbon dioxide exchange happens for the lungs, and then again these are brought back through some big size veins to the heart for pumping, and this pumping action, whatever kind of energy that is required for these kind of structures is kind of somewhat optimized kind of a pumping energy. Okay, so the nature has some ways to optimize these energy requirements for such applications by having geometry for the structures in the way it is there in the nature. So we are thinking like this. Okay, how can we fabricate such systems? Okay, so these have very high efficiencies as I was mentioning here. So people have started like fabricating these in a lab scale by on a wafer, silicon wafer to do the similar study, and then they have found that okay, it indeed this is kind of giving you efficient kind of a heat transport with a minimum energy of pumping of the fluid into these channels. Okay, these also have been found to be structurally more stable. If you see the tree structures, they are kind of stable structures for the different wind and other kind of a loading that is coming, and people have started like using that also in the structural domain. Okay, the civil construction kind of a domain where you have this multiple branch splitting happening to support the say ceiling or some other thing. So you can see there are this more of such kind of a designs people are, they are also elegant in their artistic kind of a perspective. So these designs have been coming up, and they are now, because of the 3D printing, which is very ubiquitous now. I mean, and in the future also this is the way to go. You can print this kind of a complex structures very easily. Okay. Otherwise, without 3D printing, fabricating such a kind of a structure is quite a task actually. Okay. So there are some advantages to these structures, and then the question comes, okay, how do we kind of manufacture such a structures in a very easy way? Okay, conventional manufacturing techniques are there, but now we'll see some different way of doing things here. Okay, but not at the structure kind of a big scale, but as say leaf scale or some smaller scale than that. Okay, and then we'll see how this some of the natural processes which are there can be exploited to do a good control over these structures, and how mechatronics can play a very nice role in whole process. Okay, that is how we are going to develop this talk. Okay, so if you see this, the inspiration is really from the natural phenomena. Okay, so you can see this video where like you have this kind of a patterns that are coming in some kind of a way of painting. Like how this goes is, you start off with this color palette here, and then in this you have different colors you take to mix and produce something, and you add this glue to those colors. Okay, you put some kind of a Fevicol or some other kind of a glue, and then you make this slurry a little thicker, and use that on a plate. Okay, whatever combination of colors that you want to kind of use, you may be able to use them, and then you start placing other kind of a glass plate on the top of that. Okay, so to squeeze these two things in between the two glass plates. Okay, so you see that liquid is now pressed and it is formed into a film. Okay, so you can see this somewhat circular film coming up there. Okay, of the liquid color and Fevicol that we have used. Okay, and then you simply separate these plates out. Okay, when you separate them out, you see this geometry starts coming up. Some geometry starts coming up. This is a fingering instability that happens called Safman-Teller instability. Okay, and this kind of a geometry that is coming up on this thing, that you can transfer to the paper. Okay, so so that is how you can get very interesting pictures of this kind. Okay, and so this is how it is getting transferred to the paper from the glass, and you have some interesting geometry coming up there. Okay, this is a completely natural kind of a way of doing things. Okay, so now the idea here is to exploit this process called Safman-Teller instability in this cell called lifted Hele-Shaw cell for fabricating some interesting kind of structures of branched kind of a pattern. So you understood the process that okay, you have a fluid drop which is pressed between the two plates, and then this is compressed, and then we separate it out. Now instead of doing manually, we want to do it of course in some kind of a controlled fashion, and for that we now need to design a mechatronic system to carry out that operation. Okay, and what patterns right now evolve are kind of random branches here. Okay, every time you do the process, you may not be guaranteed that okay, same pattern will come. Okay, in fact the patterns will be completely different every time you carry out that. Now we want to see that okay, these patterns are repeatable, controlled in some way, and we want to know how do we execute this process with the mechatronics. Okay, so like that we will proceed to kind of seek answers to these questions. Okay, so you also give a thought to this process. Maybe you think now based on whatever you have understood from the course, you see okay, suppose I want to carry out this, what kind of a thinking I should do, or so I would suggest you pause this video here and give your own kind of a design of mechatronic system around this kind of phenomena, and see what comes to your mind, and see then like when you see the solution, some other things may open up. So do that exercise. It will be very important to do. Okay, so so you have to see the questions like how do we do this process of squeezing and then opening up, either like the angular kind of a way of opening up, or straight parallel way of opening up. Okay, so this right now we have done whatever you saw in the video is angular way of opening up. Okay, so how do we kind of carry out this repeatedly in the exactly same manner? Okay, what you think about what is the process, or what is the kind of a mechanism, what are the actuators that we should use, what are the sensors that we will use, and how do we control, what is the control algorithm that you may have to think about. So all those details you give a good thought to that, and then like we'll see the solution. Okay, so now I'm proceeding. Okay, you may pause and think and then come back. So let us think about this mechatronics now. Okay, so your process is clear that okay, you have this fluid drop, now it is getting compressed, and then you are separating the films angularly, and this separation of these plates happening angularly is about some axis, okay, which is fixed axis, and preferably it is at the surface of this other plate. Okay, so that like the action happens really nicely. So this is what is a constraint from the design perspective, that okay, we want to open up these two plates, and this opening needs to happen such that like one plate is as if it is hinged to the other plate. We don't have a physical hinge there, we have these glass plates here, and in the glass, how you cannot produce the hinge very easily and repeatably. And also this process to have a good control, like this needs to be carried out very slow. Okay, this opening happens at a very slow speed. We want to open it up. Okay, we don't want to kind of do it at a very fast speed. So to have that control, these are like some design requirements you can bring out. Okay, as you do the process, you will find that okay, these are the important design requirements, that okay, you need to move it very slow, and then we need to have this motion happening such that there is no like the slipping motion. Okay, it's only like opening motion happening. There is no like no sidewise motion happening. Okay, or shear motion happening. Okay, so again think about this part if you have not really thought about this before. Then what we do is to use this remote center motion mechanism. Okay, so there are many different remote center mechanisms that are available in the rigid domain, rigid body domain. You check out in the website and see what are different kinds of rigid body remote center of motion mechanisms available, and one can employ them here for this process. Which will work, okay, which will work for this process well, but to move things at slow speeds, you'll have a joint friction. Okay, the friction in the joints of this RCM mechanism, rigid body RCM mechanisms, and if you want to move slow with the friction, it is very tough to do. You know that, right? We have seen that the friction model, like when you start you want to move something which is very slow speed, the things doesn't move, they'll just slip, and then again you stop, and again you some force exceeds, then like it again slips, like that. The stick slip kind of a phenomena will happen if you want to move very slow speed. Okay, so that is a problem with the friction. So now how do we overcome this problem? So then again, like we have seen, if you want to have very accurate motions without friction, you need to think about these motions without having these rigid mechanical joints. Okay, so without joints, if you want to have this motion, the option you remember what we have seen in the class is the compliant mechanisms. So flexion mechanisms is what you will think of using. And then you need to kind of say, okay, oh look, are there any compliant mechanisms which can do this job available in the literature? Then you may find some things, you may plan and use that. So we have designed in this case our own compliant mechanisms here. Okay, So you'll see in a minute how we have done that. Okay, so this is how you start this process of design of these kind of mechatronic systems in by using some of the ideas and concepts that we have learned in the course. So we want to get this very slow motion, and then that's why we are using these compliant mechanisms in the system, and then we will now use this, first see the compliant mechanism and then build system around that then. Okay, so this is a compliant mechanism, is very simple. It's like a simple cantilever link with this kind of a perpendicular fold to that link here, and that is used as a compliant mechanism for this remote center motion. So if you do the analysis of such a beam when the force is acting on it by using some standard softwares which are available in the market, the ANSYS or SolidWorks or some FEM softwares, then you'll find that this mechanism, okay, we didn't do that before. We just conceived this idea that okay, let's say if we can use a cantilever for this purpose, and then we started playing around, and then we found that okay, it is possible that this can be used, because if you do this analysis, you find that there is a point which is not really the hinge point of this cantilever, which is somewhere outside in the space. Around that point, actually the motion happens as if it the end point of this compliant link is moving around a circular arc about this center. Okay, so that is what you'll see. Some literature also, like some indications are there of such a kind of a thing, but there is in the literature it is only for the cantilever, but we are using now cantilever and some kind of a additional link, which is this is fold of the cantilever basically. Okay, so this particular kind of a mechanism has or now we can call this not just a beam, but it is a mechanism, has this remote center for motion, and we use two such beams on the two different sides of this glass plate, and use that to really do the job. Okay, so this is like a solid model for that kind of a design, and then this is actually fabricated stuff. Okay, there are glass plates, there is a cantilever beam which is fixed at some point, and we now arrange this entire kind of a fixed plate and the moving plate in such a way that the hinge is at the surface of the fixed plate. Okay, so when I apply some force on this cantilever, automatically this plate is going to move as if it has a hinge here. Okay, because it is supported now by this compliant mechanism here. Okay, so of course there may be some touch will be happening here. It's not like this is not touching the fixed plate. When the force is applied here, there will be touch of this point happening to the fixed plate, but it will as you carry out this motion, it will get lifted as if it is hinged at this point. Okay, and we have characterized this by seeing under microscope how much is there any motion happening at this point or not. Okay, all those things have been characterized to confirm that okay, it indeed moves as if there is a hinge at this point, although there is no physical hinge. Okay, so this is how we have built one part of the mechatronic system, the mechanical plant, so to say. Okay, then now we want to see okay, how do we place the actuators and other kind of stuff in the system. Okay, so we need to see now actuator, and then the actuator needs to get guided in some kind of a straight line fashion, and then so that then we'll be able to programmatically do the lifting process. Okay, so you can see here that okay, this lifting process is happening when this point is applied some force, and this point is to move in some kind of a straight line fashion. Then how do we achieve that? Okay, we want just a motion below, we in some kind of a vertical direction. Okay, at this point, as the plate moves, there is some small because this is a circular arc, this point is also going to go shift in the y direction also a little bit. Okay, so we need to have that some kind of a leeway for this point to move in y direction, but we are to apply the force in the vertical direction, and for that we can use some straight line guide for this point to move. Okay, so this is a straight line guide that is needed, and again we want this straight line guide to have we can use some kind of a ball bearing for the straight line guide. That also may work, but we are using other kind of a compliant mechanisms to reduce friction in the system, and this compliant mechanism is based on some kind of a spiral grooves in a small disc. Okay, that kind of a compliant mechanism is what we are using here. Okay, that will avoid just a friction in the bearing. Okay, but I think there is no harm, like no one can use directly some kind of a linear guide bearing, and this job will be done, no problem. Okay, in fact we are doing that in the case of our other setups, some other setups as well. We are using some kind of a lead screw or ball screw kind of arrangement to get this kind of a precision motion. So no problem. So we are using compliant mechanisms, as I said, and then this compliant mechanism will be operated by the voice coil actuator. Okay, so one can have a ball screw and a linear motor kind of a combination, not linear motion motor, the ball screw and a motor kind of a combination to give you a linear motion. Okay, so the motor is rotating the ball screw, and you get some kind of a linear motion at the output, which can be used to actuate this plate in the angular fashion, and or maybe the linear fashion as well. Okay, so this is how like we now think of like actuating this system, and the sensors in the system can be our standard linear encoders, where we can measure the linear displacement of the actuator and conclude about the angle of the lift, because here now we don't have really a shaft on which we can mount the sensor here for the rotary motion measurement. So we can measure the linear motion of the like point which is getting actuated and conclude about the angular motion of the two plates. Okay, so this is how now we put together all the parts in the mechatronic system. So you have these compliant mechanisms you can see here. Okay, so that is fabricated and it is in place for actuation. Then we are actually using also the force sensor to measure the force. So this was the first time we are doing this process, so we wanted to have entire characterization of this process to happen, and for that you need this force measurement to be done. Okay, so this force sensor, 6-axis force sensor load cell was used here between the plate, okay, and the actuator. Okay, so you have this actuator up here, where this is a coil, and then there is a magnet here, and then this is a compliant bearing or flexure bearing, which is used to just guide the block up and down. Okay, now so you can see the schematic up here. Now how do you take encoder input into? So we are using this controller as again a D-space control system here. You can use also like other embedded systems, like you can have a TIVA microcontroller to be used, and it's fine, no problem. Okay, so what we are using here is encoder to sense the position of this system. Then force sensor input is taken by analog to digital converter. So this should be ADC here. Okay, so this is ADC, analog to digital conversion is happening here, and that data is in your microcontroller. And then this is digital analog converter is used to give input to this amplifier, which will actuate the actuator. Okay, so it will flow some current in the coil, and then it will actuate the coil. Okay, so this is how this entire system can be having this closed loop. So you can close the loop based on the encoder data, or you can also based on the force sensor data you can close the loop. So we want to say maintain a constant force, that is possible with this closed loop system here. And then you of course use this camera and zoom optics to kind of observe what is happening to the fluid and see all this details. So this is how we put together the entire mechatronic system as a lab setup kind of a scale. Okay, So see again, to tell you that okay, if we want this to be like a product out, then we replace this by using our microcontroller system with some small human machine interface to operate things. Okay, so that's how, like, our mechatronic system will go as a product in this case. Okay, now let's discuss a little bit about control. What kind of a thing that you see if after seeing this system here, what kind of thoughts you can gather for really exercising control over this system. Okay, so we want to basically move this upper plate in very much controlled fashion to pull it down to execute our process. Okay, so we want to say we want to maintain some fixed velocity as we pull it down. Okay, so if this plate is pulled down, we want to maintain a fixed velocity, say 5 micron per second or 10 micron per second kind of a velocity needs to be maintained. Okay, so that we slowly kind of do this process and observe things, and we should so this need not be slow as all the time, but we have some provision to change the speed, and we say okay, no, I want to now do it at 50 micron per second kind of a speed, so I have little faster process and then I observe. So this is what is needed in the research, to kind of change parameters and observe the things, and then you start studying the processes and conclude about what is your observation and how the theory will match with your experimental findings and things like that. Okay, that's how you carry out those processes. So in this case, now your plant is this mass attached to the compliant elements of this flexure bearing. Okay, so these are so you have a force sensor also is a part of your mass, and then your plate and things also are part of the mass. But interestingly here, so it's just the inertia that is there, or there is something more to that. So when we are operating by this actuator, is just the inertia of these elements that is coming in picture, or there is something more to that. See, of course, the liquid that is getting squeezed is going to apply some forces. Okay, so do we know those forces? Those are kind of questions will come to mind to see, okay, that if I want to design control, that control should be robust to these forces. Otherwise, I design some control action, okay, and the gains are some chosen gains. But moment this liquid separation force starts coming in picture, when I start separating, then this controller will start giving error. It will not move the system anymore at 10 micron per second kind of a speed that I desire it to move. Okay, so those kind of things are going to happen. So this is going to be some kind of a disturbance rejection kind of a control you need to have, because you don't know a priori what kind of a fluid force is going to come. Okay, it will change from fluid to fluid, and from experiment to experiment also there might be some small changes that will be happening. So that's where the feedback concept comes into picture very handy. Okay, see we have designed, other point is we have designed this system such that there is no friction in the system. Okay, so then control at low velocities will be relatively easy. Okay, the fluid is giving some friction, but that fluid friction force is usually as a viscous friction force. Okay, it's not a Coulomb friction kind of a force. Okay, so that's why you will not find a stick behavior offered because of the presence of the fluid. Okay, this and we are avoiding the stick slip behavior because of the two solid components that are rubbing against each other. That kind of a Coulomb friction we are avoiding by using the compliant mechanisms in the design. So this is a kind of a way we can see that the concept of design in mechanical domain, which will ease out some part in control or some part in the electronics domain, has happened here. Okay, so the way we did the same thing for the 3D printer case, or you observe the similar kind of ideas in CD-ROM drive. Okay, these are the kind of ideas that are to be employed to make sure that you are giving a complete system solution. Okay, not in mechanical domain separately and in the electronics domain separately. Okay, this is how we will think about in the as application of the concepts that we are learned in this course in the practical interesting kind of a system example. Okay, and these ideas can be borrowed to many other systems that you say in your future activities, wherever you are kind of going, you'll have an opportunity to work on such a systems, and then you can give some elegant solutions to your problems. Okay, and of course you can contact us anytime if you are in need of such kind of solutions. Then this we see now some of the results, okay, of the control. So control is done in a way that, okay, while squeezing, we are squeezing from this point A to point B. So this is a displacement, or the plate position in mm kind of a displacement of the point of the end. Okay, so we are not plotting the angle here, we are plotting the point of the motion of the actuator. Okay, actuator moves, the squeezing happens, and like you'll get this point here. Okay, this is displacement of the end point here. Okay, so you squeeze it, and then the squeezing happens with a constant force. So we have programmed the thing such that we squeeze at a constant force, so that this squeezing happens. We don't worry about the displacement at that point, but only while separating. So then there is some delay for the fluid to get relaxed. Okay, so we provide some delay for the fluid to get relaxed, and at point C the control is switched on. Okay, and this control is simple PD kind of a control is there, PD PID kind of control is there, that is switched on to kind of get the lifting done here. So the lifting is shown in the bottom side motion of the bottom, or downward motion of the thing. Upward motion is squeezing, and downward motion is lifting or separation. Okay, so this is how we design the plan for the experiment. So if you see what is happening to the fluid droplet is between the plates. It is not yet squeezed. From A to B it will get squeezed, and it will form a thing like a film of the fluid, and then from C to D the separation happens, and you get this kind of a patterns that are produced on the surface. Okay, so these patterns are what we are interested in to study, okay, how these patterns can be evolved with the controlled way, and how these patterns can give us some application kind of a structure. So say for example these structures, if I take and solidify, okay, they are liquid to begin with, I solidify by some means, and then if I solidify, then they can be acting as a microchannels for studying the microfluidic kind of processes, which are similar to what they are there in the biological systems. Okay, so we can biomimic the some of the devices or some of the organs that are there in the biological domain. Okay, so this is a very interesting way of mimicking what is there in our nature. Many different systems are there. Those systems can be mimicked, and they can be studied, and after studying, we can make use of them in the application. Okay, so let's see say when you carry out this process, we will see now what happens to the force, because we are recording the data on the force sensor. We can look at that data. So you see this data is coming as an analog force sensor. So this data is a little bit noisy. This is I think this is after filtering further. Okay, so we have used some kind of a moving average filter to filter out the data and remove the some of the noise, but still you can see some noise will be still there, because the analog sensors are prone to pick up noise from many environmental places, as we have seen. And we need to employ some kind of filters to filter out that noise, making sure that your data that you want to preserve, okay, or you want to look at, okay, the data frequency and the filter frequencies are not messed up in some way, in the sense your as we have seen in the previous lectures, the filtering is done at much higher frequency than what data we want to look at. Okay, see this highest frequency data is not what we want to look at. What we want to look at is, okay, what is this low frequency stuff that is coming up as we carry out this process. Okay, so that's where you filter out this very high frequency data, and it has been filtered out, and it has gone down a little bit, but you cannot have it completely zero. Okay, now so when we start squeezing, this force starts increasing. Okay, so this force increases up to point about 11 Newton force, and then we stop squeezing, then the fluid relaxes and the force comes down to about 4 Newton. Okay, so this is a delay part. Okay, and now we start giving a control to separate it out, then force further drops, and then it comes to some level here, and then we are carrying out the separation in this domain. At some point the force will also you'll see that force may go a little bit below 0 also. Okay, so that is how you read this graph and conclude about okay, what is happening in the fluids. Okay, so about maybe halfway through the process you will find this force has gone down, force is below 0. You are actually pulling the liquid out or creating some kind of a vacuum inside the liquid, or pressure that is lower than atmosphere inside the liquid. Okay, and overall you can see that the lifting force is much smaller than the squeezing force. That's a very important conclusion that we got from this process. So that when we want to scale the process up to kind of much larger kind of a dimension, we need to be worried about how do we squeeze, because our actuator design will be based on this force. Okay, so we are able to kind of squeeze more. Then you want to squeeze more, then or thinner kind of a film, we need much kind of a higher actuation force there. Okay, so so these are different kind of a domain of analysis, saying that okay, in the fluids domain, how much force will be required to squeeze a film to the thickness of say 20 micron or 30 micron or 50 micron or 100 micron. So we go lower in the thickness, our force will start more and more. Okay, so this is kind of obvious, but what is not obvious is how this force scales. Okay, how much force more I'll need to apply, or what is the quantitative aspect of this. That is a very different domain of fluid dynamics working. So here you can see now this video for angular lifting. Okay, so you can see before playing video I'll show you, this is a point where the force is applied. Okay, so when you squeeze, the plate is squeezed here, and then there is no contact between this some small gap is maintained there, and as you start separating, this gap will be absorbed first and then this plate. So you can see this is an acrylic plate up here. This is our mechanism, which is having a fixed point here, and that fixed point there, this kind of a mechanism design is such that it creates a hinge point at the end of this plate here. Okay, so you can see that kind of a lifting happening. So part of the lifting, you may not be able to see the complete plate because only the lower part of this plate is getting seen here. There will be some part which is hidden behind this ring. Okay, so let's observe that. So you can see as a squeezing starts, this gap will be, as a separation starts, this gap will be absorbed. Okay, and then now this is lifting. Okay, so this has lifted completely here. Okay, so this we don't want much angle to lift here. We want just a small angle so that this film gets separated. So 2-3 mm kind of a motion is sufficient here. Okay, so this is how this setup is now working. Okay, then what we can do about that we'll see in a minute. Okay, so this is another kind of a mechatronic system, which is a parallel lifting kind of a system. Okay, so we will not get into too much detail about that, but only thing here now, the actuator is different. Okay, instead of the voice coil actuator, now we are using a translation stage. Okay, so here we are using this stepper motor based translation stage from the hallmark thing that we discussed in the class at depth. So this stage is giving us a possibility. So this motor is a stepper motor, which is having a torque which is much higher than the friction that is there in the system. So we have seen that with the micro stepping kind of a driver that is used for the stepper motor, we are able to kind of move this plate parallel to the other plate in a very smooth fashion here. Okay, which is acceptable for our experiments. That's what I can say. It will still have a stepping kind of effect, very small steps. I mean, there will be some micron or sub-micron kind of a steps will be there, but that is not really bothersome for our experimental observations to really get to. So that's why I said, like, we can have actuator both as that voice coil actuator also possibility, or we can use these stepper motor kind of actuators also. So here there are these ball bearings to kind of guide this in the vertical direction down, and stepper motor to actuate. So a lot of friction is existing in the system, but that is getting overcome by the stepper torque, and even then we are able to move in a small steps at a very slow speed. So this action will happen now as a small steps. Okay, so this is not really kind of a continuous smooth kind of a motion, but it is going to be in a steppy kind of a fashion. But since these steps are very, very low in size, we don't have any problem in really executing this setup. Now what we have done with these setups, so both of these setups are like developed in house for as a mechatronic system, and what we can do with these setups is what I'll talk about a little bit now, to give you some kind of a sense of what interesting the ideas or fabrications these setups can do. So this is where, like, we introduce this. You see this video here. This is now top camera recording this thing, where the squeezing happened just now. Okay, the squeezing of the film has happened here already, and there are these small little trenches that we have machined on the surface of this plate, one of the plates. Okay, and then you can see that now the fluid, the air starts penetrating through those trenches preferentially. Okay, with this air penetrating that through them, they are designed to kind of do some kind of a dimensions, so that, like, this air doesn't progress too large in this plane, but it in this kind of a air finger progresses much larger distance, and this progresses much larger distance. This progresses even larger distance than that. Like that, we have designed these trenches to be. Okay. So with this, we are able to now produce, like, the controlled structures, where you have one branch splitting into two branches only, and then further splitting into two branches only, further splitting into two branches only. But at the other place where we didn't have this anisotropies on the cell plates, this is a random process is happening still. Okay, so this is how we exercise additional control. Okay, so the control that we had so far was only the speed of the plate for motion. Okay, now we have these additional controls that are coming up by virtue of some kind of anisotropies on the cell plates. Okay, so in the form of these pits or holes or some, so these plates are no more planar plates. These are like having some holes, and now we are using acrylic plates, so that we are able to see through the plate to see what is happening to my fluid, and also we are able to machine these acrylic very easily. I'll show you, like, how this entire process goes in a minute. Okay, so now let's see this kind of a topology is coming up on the so this one can see that this can be scaled further and do a lot of different things with this. Now we have this picture which shows that, okay, we have this by studying this process phenomena in much more detail in the fluid dynamics kind of a domain, which we are not interested right now, because we are, like, looking at from mainly mechatronics perspective, but we are able to fabricate then, like, these multiple generations of the split. Okay, so this is like first split here, second split here, third split here, fourth split here, and fifth split here. So like 5 generations we are generating these fractal geometry structures, and this process can be useful for as I said, like, some biological kind of applications. Okay, now this is under alternate control, another control that we are exercising by putting them holes now instead of just at those kind of scratches or some kind of pits. Now these are holes, completely through and through holes, and they are allowing the fluid, the air fingers to grow. Okay, So how do we kind of make them grow more or less? Like, there are a lot of some kind of a study has been done about that, and all these kind of things are arranged in a way that this kind of complete symmetry of the structures can be possible to be produced. Okay, so again the process exactly is the same. Like in the mechatronics kind of a perspective, we are still squeezing the fluid and then separating it out. Okay, that's it. Okay, but now they are able to produce with that process very interesting kind of structures, and these structures can go with the array kind of a pattern. They can go as a full triangular array of fluid, and then further like an hexagonal array or some other kind of possibilities that can be there. And this can be done now on much larger scale, as long as we are able to manage the big size scale, big size plate motions. This can be done at a much higher kind of a scale. Okay, so the scalability is there inherent because it's just a fluid that is going to be working there in all places. So we have worked out some kind of a non-dimensional numbers under which these processes will happen very easily, and things like that. In the fluid domain, what are the non-dimensional numbers governing the case? So if you have, in case you are using your own fluid, you know what are the properties to look for and things like that. Okay, all those details can be found in this paper. Okay, and then these are multiple kind of versions of such structures. Okay, different patterns. Okay, and then you have this with the multiple holes now. Instead of just holes on the periphery, we are using now holes everywhere. And then what are the pressure curves that this is a cross section of the this is like showing the pressure that is built up inside this film, like a parabolic kind of a fashion. But when we have these multiple holes, then the pressure built up doesn't happen so much. Okay, and many places you will have this wherever these holes are, you have atmospheric pressure there. Okay, which is like in a horizontal line here. Okay, so these pressure gradients, as we saw already in the previous video, this is also working now for giving you these different kinds of patterns. Okay, you can see here this triangular shape patterns, and we'll show some other patterns also. Okay, so let's see, these are the other patterns that can be produced. Okay, you can get square patterns, you can get hexagonal patterns, and you can mimic the lift completely. The lift veins, we took this image, and by processing image we found out what are the anisotropies that are to be there on our cell plates, and we can produce that also, reproduce that also. Okay, so here is a thing, this image is missing here, but that image was showing actually the reproduced part of these veins. Okay, so then the total summary of this process is somewhat captured here. Okay, you can see this video now. Okay, so this starts with this one setup here that we just saw in the previous slides also, and the process starts with this modifying the cell plate. So you can see this is a cell plate here, and it is we have this home developed micro drilling kind of a system here. Okay, so we have used these motors for this from the aero modeling, the propeller motors, and one can have very high speed for those motors, and we can design this kind of a again mechatronic system of drilling holes, micro holes, which is done in house. Okay, so now we have put a fluid droplet here, which you see this upside down droplet up here. Okay, and we will start squeezing that droplet by giving now the rotation to the ball screw. Okay, and in this fluid film is now droplet has touched, and then fluid film is getting squeezed. Okay, this fluid film gets stretched, and then it touches these holes as we saw, and then we do it at a high speed, we will not get the geometry that we want. Okay, we do it at a slow speed, or the speed that we have calculated a priori, and then this geometry starts coming up in the thing. Okay, so this is how you see that. Now you can see many different kind of geometries that are fabricated by this control. Okay, and this is a different setup. So you can see this is a flexure bearing up here. Okay, so maybe we can go back a little bit and then see this spiral flexure bearing. Okay, so let me pause here. Okay, you can see that these are spiral grooves here for the bearing. Okay, the spiral grooves in the plate can allow this up and down motion happening. Okay, and such kind of a bearing is there at one end and at the other end, and these two ends will constrain it to move only in a straight line up and down. Okay, so this is how the angular lifting setup that mechatronics we have seen, and then this is a experiment with that. Okay, so maybe we just I think we have seen. So this is, see, this is if you don't have any anisotropy, okay, or you don't have any control, this is how the very slow, the process is moving very slow at whatever 5 micron, 10 micron per second speed. You see these fingers evolving in real time right now actually, and then they evolve, and like then they form some patterns on the surface. Okay, this is without control, and then we have with control we have these ordered kind of a structures here. Okay, and then different patterns coming up here. Okay, so this is what we have seen already, some part. Okay, so maybe I think we can skip the rest of the part. Okay, you have these different interesting patterns that can be fabricated, and one can explore this more. I mean, with different kinds of fluids you can have different possibilities. Say for example, if you use evaporating kind of a liquid, okay, evaporating solvent is evaporating, then you get these kind of a patterns. Okay, so this is a combination of liquid drying on the surface and this Hele-Shaw process. Okay, so these kind of patterns are very easy to get in this process, and then we can invert this by casting in the material called PDMS. This is a kind of rubber kind of a material in which this can be casted, and then this can act as a microchannels. Okay, so these things will act as a microchannels of different cross sections. So we have one of the applications with one of the collaborators, Professor Abhijit Mujumdar from Chemical Engineering in IIT Bombay. We are developing a platform for drug screening or chemotaxis. Okay, so we will not get into the details of this application, but the point is to say that okay, this is kind of a research will lead to some kind of applications eventually. Okay, this is another application where we have a leaf mimicking micro pump. Okay, that has been developed here. Okay, so so there are many different application possibilities and collaborative possibilities for such a kind of a work, and we can explore those in the future in more detail. Okay, so say for example, there are this condensation over this fractal geometry or heat exchangers with this kind of geometry. There are some of the kind of sensors with this or energy applications, solar electrodes, or even the electrodes for water splitting to get hydrogen generation or hydrogen production done. Like there are a lot of different kind of possibilities that exist, and some of them we are exploring in our lab, and you feel free to explore what you want to and then feel free to talk to us if at all you want to have some application to be done. Okay, so this is the team that has worked behind this, and we must acknowledge like Imprint Grant which funded this project, and these are my collaborators, faculty for this particular part. Professor Amitabh Bhattacharya, we are collaborating for the theoretical kind of aspect, and Professor Abhijit Mujumdar from Chemical Engineering for bio applications in this domain. And these are, of course, is a big team of the students and research RAs and PhDs students who are working behind, although I am getting an opportunity to present this work to you. Okay, and then there are industry collaborators like Dr. Dhananjaya and Menon from Strategy Automation, and Dhananjaya from Ashira Labs. Okay, so some bioapplications future development we are doing with them. Okay, so thank you very much, and I'm hoping this course will give you a good lead in developing your own kind of mechatronic systems in whatever application areas that you're developing. Thank you very much. Bye bye.